Good morning, I'm Bompard. I'm going to introduce to you our work about competition and cooperation of the energy commodity in the energy transition. The idea is to see which can be the most preferable mix in terms of energy commodity for facing the challenges of the energy transition, a kind of energy cocktail for the energy transition. I will try to introduce you briefly the framework for the analysis, the goals of the transition, because we want to achieve, and then define the energy chain that is the basis for an energy comparison of the different options we have for the commodities. I will try to draw some conclusive remarks. The game of energy is something like what is represented here. So from one side you have the primary energy sources that are renewables or not renewables, and the challenge in the transition is to move from non-renewables, fossil commodities, to the renewables ones. To the right you have the final uses that are characterized in terms of services provided to the users. So can be residential, in the residential domain, can be in the commercial and services domain, can be in the transport or industrial processes. And in between you have the commodities, electricity, heat, petroleum products, synthetic gas, hydrogen, solid fuels and biofuels that can be seen both as energy commodities for the final uses and energy vector for transferring energy from the primary sources to the final uses. So basically the challenge here is to map the energy sources onto the final uses of energy. The final uses are not expressed strictly in terms of commodity, they are expressed in terms of services, as we saw. And the same final use can be in principle fed by different commodities that can compete to provide that service. So we can have an interchanging commodities both in terms of energy vectors and energy for final uses. They are interchangeable, but as we'll see in this presentation, there are some of them that maybe are most preferable alternatives, and electricity is among them. However, not all the commodity, even electricity, are suitable for all the final uses. So this is the bigger question we want to face. The scenario we are facing is the one depicted in these slides. So you have primary energy sources, maybe renewable or not, that are strictly linked with a native commodity. So if you have PV, you get electricity. If you have solar thermal, you get heat. If you have biomasses, you get chemical energy. And on the top, on the bottom, you have the final uses that are defined in terms of service and devices that can transform the commodity in the service we need. We have the 5 main commodities: electricity, natural gas, hydrogen, heat, and biofuels, that can be applied to satisfy different final uses, and are the energy vectors. And then you have some conversion chains. That is what makes the energy chain altogether. So I can get electricity from PV and use directly as electricity, or I can convert to green hydrogen through electrolysis and then use as hydrogen, vector and final uses, or I can convert hydrogen into synthetic gas through the methanation process, adding CO2. And again, I can use synthetic gas as a commodity. In general terms, the main objectives, the main goals we want to achieve in energy transition are related to well-known energy trilemma. So it's a security, very important and, let's say, hot topic in the present geopolitical situation. Energy sustainability means CO2 and pollutant reduction, and equity, the possibility to make energy affordable for everybody around the world. The challenge is in the fact that from one side, many countries, especially European Union, are setting very ambitious targets in terms of decarbonization. And that means to move from non-renewable to renewable energy sources. This is from one side. From the other side, we have a maximum amount of capacity from renewables that we can deploy every year. So basically, this is a bit of contradiction, a bit of mismatch about the pace we would like to have in terms of decarbonization from one side, and the pace we can deploy capacity that is fitting with those goals. From this perspective, the idea of energy mix of commodities is even more important. If we wanted to think about a framework for the assessment of the transition cocktail, we must keep in mind the different dimensions. One is the energy efficiency, and this is the one we will focus on in this presentation. But there are also the energy security and sustainability we already mentioned, also socioeconomic aspects, the impacts of the transition on the level of employment and of the social and economic structure of a country, and then of course the technological readiness, so which kind of devices to transform commodities in final uses are presently available. Altogether, an in-depth analysis of the best mix of commodities is surely needed, and every commodity should have a proper role. And from this there is the idea of cross-sector coupling or cross-sector integration. So how I build this right or the best possible cocktail for the transition. Trying to make the analysis of the first dimension in terms of, let's say, energy perspective, we introduce the concept of energy chain, in which basically you start from the prime energy source, and then you might have a conversion. Eventually you get electricity, you transform that in green hydrogen, and then you have the storage. One of the crucial issues in exploiting renewable energy sources is that they have power output that are quickly changing over the time. They are not or very low predictable, and so for sure you need the storage. And again, the storage can be electrochemical, can be hydrogen, can be gas, or whatever. And then when you use the commodities energy vector, you need to have infrastructures, transmission and distribution, that are in charge of transporting and delivering the commodity to the final uses. At the end, you have the transformation at the premises of the user, in which you convert the commodity into the service the user needs. The analysis we are going to undertake, that is necessary because we want to have a quantitative and comparable analysis to find the most suitable commodity mix, is done based on ranking the commodity chain according to two assessment criteria based on the thermodynamics. So basically, one is the first principle, energy, the second one is the second, is exergy. Of course, this is not the whole picture. We need also to take into account, as we will see in our conclusion, economic and environmental aspects along the chain, but we do not focus on this in this presentation. So actually, we fix about energy efficiency and exergy efficiency. For this reason, we consider a set of stages that are the different steps we go through in the energy chain. And in this respect, each stage is represented by an input of energy or exergy and an output. And then we have a value of the efficiency of energy or exergy in that stage, and the cumulative energy of exergy available after that stage. So in terms of chains, here you see an example of chain, of energy chain, for a specific final use, that is space heating and cooling. So you have on the left-hand side the prime energy source, renewables. We have a fossil commodity like natural gas as a comparison. And then you have the different stages we set, and different converters, heat pump, condensing boiler, electric boiler, and so forth. So in some cases you have all the chain that is based on electricity. In other cases you have the conversion, like in this case, and you get the green hydrogen. And you see here the difference in let's say, efficiency, how much kilowatt hours we can get for the final use out of 1 kilowatt hour of prime energy source. And you see how electricity is pretty competing. But the same here, you see, is another final uses, is light-duty vehicles. And again, you compare the exploitation of a chain based fully on electricity, as a reference the natural gas, and a couple of chains in which out of the electricity from prime energy sources you get hydrogen and then you use for the cars, like a fuel cell, so with electric motors, or as an internal combustion engine fired by hydrogen. And you see here the difference in terms of the energy performance of those different chains. To summarize here, we can say that heat pumps are the most energy efficient device for space heating application, while gas-fired condensing boilers and electric boilers require more or less 3 times larger prime energy supply to provide the same quantity of energy to the final uses. And hydrogen-fired boilers need almost 6 times higher amount of energy. The electric motor is the best performance device in the transport sector, as it needs less than half the amount of energy required by a fuel cell vehicle, and around 1/4 of the quantity of energy withdrawn by an hydrogen-fired internal combustion engine. You see here the situation represented. If we move to the second principle of thermodynamics and we look to exergy, again we are basically the same representation of the chains, the same chains we saw before for space heating and cooling. In this case, they are characterized in terms of exergy. And the same chain in terms of exergy can be also considered for the light-duty vehicles. So again, here, if you want to conclude this comparison, we can say that heat pumps are better devices than boilers because combustion are among the most exergy-destroying thermodynamic processes due both to fluid mixing and not stoichiometric air-to-fuel ratio and the useful heat that is lost in terms of combustion products. And for the same reason, the electric motors perform better than the internal combustion engines, and generally speaking, they are preferable alternatives because they convert electricity into shaft work, hence the income pure energy flow is not downgraded to less valuable sources of energy. Fuel cells have an intrinsically higher exergy efficiency than internal combustion engines, but the hydrogen chain pays the price of the electrolysis conversion step. Number here, to summarize what we said, you see that heat pump is almost 3 times better than internal combustion engines, 3.1 of electricity heater, and almost 6 of the condensing, 6 times the condensing boiler. For the electric motor is almost 2 times the internal combustion engine, 2.5 the fuel cell, almost 4 times the internal combustion engine based on hydrogen, the blue ones, and based on gas, the yellow one. This fact of the efficiency is also very important because for producing electricity, energy, but in this case electricity, from renewable energy sources, PV panels or wind turbines, you need a portion of land. And so, if you have a more efficient energy chain, to provide the same service to the final user, you need less exploitation of land. And you need lower capacity, lower installed capacity from renewables, and you can maybe keep the pace of the transition according to the objective you set in a more easy way. Just to conclude, electricity stands out as a preferable commodity in the transition cocktail. It can be directly harvested from environmental sources, so we get directly from PVs, we don't need to convert. It does not require any conversion process, so we get higher efficiency. It has the same value of mechanical energy and is better also from the exergy point of view. Commodity chains that do not involve combustion processes are usually better for the higher energy efficiency. As commodity, hydrogen lags behind electricity and gas because of the electrolysis, which is both energetically and exergetically inefficient. However, there will be a considerable role for hydrogen in energy transition, especially in terms maybe of storage to cope with security issues and storage issues for energy. A complete and exhaustive analysis should take also into account other aspects, not only the energy perspective we adopted in this work. We need also to consider, we already mentioned, say, environmental and socioeconomic aspects, and the work for doing this is presently underway. Let me conclude sharing with you the whole team that worked at this project and is still working